I welcome you in today's session of physics. And in physics, you know very well, we were discussing a topic electromagnetic waves, which is your chapter number 14. We had covered out most of the things of this chapter in our previous lecture, which is lecture number 1. Now, today, this is the lecture 2, and we are going to start from the relation between magnitude of electric and the magnetic field in free space. You can see here, this is the topic we have to take today. So we are getting started. You can see here, suppose that the sinusoidal electromagnetic wave which is propagating in the free space along the positive direction of x-axis with a wave number how much k and angular frequency is omega. So the magnitude of electric and the magnetic field acting along the y and z direction respectively vary with the x and t and can be written like this equation. These are the two equations, first for the electric field and the second for the magnetic field. Clear? From this equation you can see here, these are the first one and the second one. E naught and B naught are the maximum value of the amplitudes of electric and the magnetic field respectively. Now you can write here, k is your variable is the wave number, so we can write it like k is equals to 2 pi by lambda, and omega is the frequency, so we can write it 2 pi nu, where nu is the frequency and lambda is the wavelength. So if we divide angular frequency with the wave number, so what we get here, we get here the speed of light, which is nu lambda, which is equals to c equals to nu lambda. You have read this about c is equals to nu times of lambda. Clear? Where c is the speed of light of the electromagnetic waves, which is the speed of light in free space. Now this is the equation 1 and this one is equation 2. So from equation 1 we can write it, the partial differentiation del E by dx is equals to minus k times of E naught cos omega t minus kx. And if we differentiate partially equation number 2, so we get the same thing, omega b naught cos omega t minus kx. So making this substitution in the relation, you can write here del E by del x is equals to minus del b over del t. So we have here we use the Maxwell equation, this one. So we put the value of del E over del x and del b over del t and we compare both the equations. So finally we get here E naught by b naught is equals to omega or by k, which is equals to the speed of light. Since E and b are in phase, so we can write here E by b is equals to c. Thus the ratio of the magnitudes of the electric and the magnetic fields equals and the speed of light in free space. Now this is the topic 6, energy density in electromagnetic waves. I am skipping this is not so much important, you can read by yourself. After that there is a thing given here, important characteristics of electromagnetic wave. I will tell you about the 3 or 4 what are the properties, and after that I am moving to the next topic, which is the transverse nature of electromagnetic wave. So here you can see, this is the important characteristics of electromagnetic waves. The first one, the electromagnetic waves are produced by accelerated charges, means the charge which is in motion. These waves do not require any material medium for their propagation. These waves travel in free space with the speed of light, which is 3 into 10 to the power 8 meter per second, and given by the relation this. Light waves are electromagnetic. The direction and the variation of electric and the magnetic field are perpendicular to each other and also perpendicular to the direction of propagation. This thing we already discussed. So thus electromagnetic waves are transverse in nature. Now come to the sixth one. In free space, the magnitude of electric and magnetic field in electromagnetic waves are related by E by B is equals to C. Clear? That is, the energy in the electromagnetic wave is divided on the average equally between electric and magnetic field. So you can write here UE is equals to vector of UN. And this is the energy density, which I skipped the topic. Electric field in vacuum is how much? This. And in the magnetic field it is this. So energy associated with the electromagnetic wave, you can write it like this. Clear? So now come to the transverse nature of electromagnetic waves. So here you can see, this is the figure given. Let us consider a plane electromagnetic wave propagating along x-axis. From the figure you can easily understand it. So the wave front will be a plane 1 parallel to the yz plane. So for any position of the wavefront, the electric and the magnetic field, which is E and vector B, will be 0 on the right of the wavefront, while to the left of it the value of E and B will depend on the x and t, but not upon y and z, because we are considering a plane wave. So to establish the transverse nature of the electromagnetic wave, we shall show that Vector A and vector B are perpendicular to the direction of the propagation. So from this figure you can easily understand. So let us consider an elementary parallelepiped ABCDEFGH with the sides of dx, dy and dz parallel to the xyz axis. So suppose the wavefront reaches the face EFGH at any time and the field vector E and vector B are 0 at the right of EFGH, so while of the left of the value will vary with x only. Now since the parallelepiped does not enclose any charge, so according to the Gauss law for electricity, the total electric flux through its 6 faces is 0. Clear? This is your Gauss law, close integration E dot dA is equals to 0. So if we consider for all the surfaces and finally we add up. Since vector E does not vary with y, the electric flux through the faces this BCGE and ADHE normal to the y-axis are equal and opposite, and hence contribution of the third and the fourth integration mutually cancel. Similarly, the contribution of the fifth and the sixth integral mutually cancel because vector E does not vary with the z also. So the last equation reduces to this form. Now if Ex and Ex dash be the value of the x component vector E and at the faces ABCD and EFGH respectively, then we can write here this equation or integration like this, where dy and dz is the area of each face. The minus sign arises from the negative direction along x-axis of the outward normal to the face ABCD. So this first equation comes out to be like this: minus Ex dy dz plus Ex dy dz is equals to 0, or Ey minus Ex is equals to 0. This is the relation. Clear? Now come to the possibility of Ex dash is equals to the Ex means that the electric field is static, but a static field cannot propagate a wave of finite wavelength. Hence the possibility is ruled out, and we concluded that Ex is equals to 0 and Ex dash is also equals to 0. It means that the electric field vector E has no component parallel to the direction of propagation. A similar argument for the magnetic field. Clear? Hence we concluded that in the electromagnetic waves both the electric and magnetic fields are perpendicular to the direction of wave of propagation, that is electromagnetic waves are transverse in nature. This is the important one. I hope you understand it. Now we are coming to the electromagnetic spectrum. This is also important, and most of the wavelengths things or value are asked in the examination from this. So the sunlight visible spectrum discovered by Newton extend in wavelength roughly from 4 into 10 to the power minus 7 meters. The violet spectrum is this in the red region. So after Newton it was found that the sun spectrum is not limited for violet to red region, but is considerably spread below the violet region and also above the red region. So these parts of the spectrum are visible by our eyes, so they called as the invisible spectra of the sun. The part of the smaller wavelength below violet is called the ultraviolet spectrum. This thing you kindly note down. And that of the longer wavelength above red is called the infrared spectrum. Clear? So the smaller wavelength which is below the violet is considered to be the ultraviolet, and the wavelength of red which is above is called as infrared spectrum. Now in 1865 Maxwell formulated the basic laws of electromagnetism in 4 equations which we had already discussed, known as the Maxwell equation, and predicted that the light is an electromagnetic wave. Thus in Maxwell time visible light and the ultraviolet and the infrared radiations were the only electromagnetic radiations known. Now after Maxwell death in 1888, Frank Hertz, you know the Hertz is the unit of frequency, is given by the scientist name which is known as Frank Hertz, for the first time generated and detected electromagnetic waves experimentally. So these waves are about 6 meters in wavelength and were called radio waves. Now later on were discovered X-rays and the gamma rays. These are also found to travel in the free space with the speed of light and thus electromagnetic in nature. So the range of wavelengths of all these radiation is very large, and on this basis they have been given an order. This order is called the electromagnetic spectrum. You can see here this is the figure of electromagnetic spectrum. So it ranges from very small gamma rays to very long radio waves with the overlapping region and no gaps between. The visible spectrum is only a very small part of the electromagnetic spectrum. This is the spectrum. I hope you understand it. Clear? Now, the wavelength range frequency range, methods of production, properties, and uses of various regions of electromagnetic spectrum are summarized below. So first you see the gamma rays. What is the wavelength? Is of 10 to the power minus 14 to 10 to the power minus 10 meter. And what is the frequency range? 3 into 10 to the power 22 to 3 into 10 to the power 18 hertz. Clear? These are the production and the properties. You can read it by yourself. Now I am moving to the X-rays. What is the X-rays wavelength? 10 to the power minus 13 to 3 into 10 to the power minus 8 meter. And its frequency is about 3 into 10 to the power 21 to 1 into 10 to the power 16 hertz. Clear? These are the some uses of X-rays in science, in surgery, in engineering, and in radiotherapy. Come to the ultraviolet radiation. Kindly remember this frequency and the wavelength range because it might be asked in your examination and you have to write down all those values. The wavelength range of ultraviolet region is 6 into 10 to the power minus 10 meter to 4 into 10 to the power minus 7, and same for the frequency. If we talk about 5 into 10 to the power 17 to 7.5 into 10 to the power 14 hertz. Clear? Now come to the visible light. The wavelength for the visible light is 4 into 10 to the power minus 7 to 7 into 10 to the power minus 7 meter. Its frequency range is 7.5 to 10 to the power 14 to 4 into 10 to the power 14 hertz. Clear? This is for the visible light. Infrared radiation is wavelength is this much, 7 into 10 to the power minus 7 to 5 into 10 to the power minus 3 meters. Its frequency range 4 into 10 to the power 14 to 6 into 10 to the power 10 hertz. Clear? Now this is the microwaves or short radio waves. You can see that. So its wavelength is 10 to the power minus 3 to 3 into 10 to the power minus 1 meter, and its frequency range is 3 into 10 to the power 11 to 1 into 10 to the power 9 hertz. Clear? Radio waves and long waves, these are the remaining two waves. Wavelength range is 10 to the power minus 1 to 10 to the power 4 meters, and its frequency is 10 to the power minus 3 into 10 to the power 9 to 3 into 10 to the power 4 hertz. Clear? These are the production and the uses. Now come to the long waves. Its wavelength is 5 into 10 to the power 6 to 6 into 10 to the power 6 meters, and frequency range is 60 to 50 hertz. Clear? So these are the few ranges and the frequency and the wavelength ranges of different waves. So you have to remember all these because it is important one and also can become into your examination. So this is the end of your chapter, students. We will come meet you in tomorrow's lecture with a new chapter. Clear? Till that, revise this whole chapter, and if you have any doubt, kindly ask me in the comment section. So for today, I am winding up this session. Thank you, class. Thank you very much.